Okay, friends, I guess we'll go ahead and get started. People at home, you can hear okay? We good? Yeah? All right. Thank you. So, in between class, just sort of had a proud dad moment. My son, Dallin, who's 12, texted me. He doesn't actually have a phone. He has a decommissioned phone, which he reminds us about all the time, that he doesn't get cellular data, but he can text. He is frequently requesting purchase of various things on iTunes. So if it ever pops up here, Dallin would like to buy whatever, buy Post Malone featuring whoever, you'll know, and I'll just deny it out of hand. But in any case, proud dad moment, he said, today in science, I made a chemistry joke, but I didn't get a reaction. Yeah, see, there we go. It's just, he's learning to do dad jokes, and it just is very good for my heart. He and I sometimes have conflicts. We don't see eye to eye. Someday I'll tell you about the horrible day when we were in Paris, France, and I wanted to leave him there. Anyway, Diet Coke actually saved the day. So prayers aren't answered. Diet Coke is good. Anyway, where were we? All right. So last time when we met, we were talking about identifying Homo and Lumo in organic molecules. And some of you have asked, how would you do this in a molecule where you've got multiple reasonable choices? So as an example, what if you happen to have this molecule which has an OH group on one end and an NH2 group on the other? Just as a preview of chapter 3, where we'll spend almost no time on nomenclature, OH groups are called alcohols or hydroxy groups. NH2 groups are called amino groups or amines. You've got lone pairs on the oxygen and 2 lone pairs on the oxygen and a lone pair on the nitrogen. How do you tell which one's Homo versus Lumo? Well, first of all, I'm not going to ask you to make that decision in a Homo-Lumo problem. Nevertheless, there is a way you can figure out which of those electrons is more reactive, which of those electrons is higher in energy. And we're going to develop those tools in chapter 2 and beyond. And that's going to be really helpful in helping us to predict what happens in organic chemistry reactions. And it turns out the tool you have for this is something you've had all along from general chemistry, and that is thinking about acids and bases. So I'm going to show you an acid-base equilibrium that happens when you take HCl, which is a gas, by the way, and you dissolve it in water. And hopefully in doing this, I want to dispel a simplified notion that you may have picked up in general chemistry that isn't really relevant to the world of organic chemistry and the world of reactions in water. How many of you remember learning that HCl was a really strong acid because it dissociates into H plus and Cl minus? Or maybe, and I'm really not trying to throw my colleagues under the bus. They do a great job in general chemistry, and high school teachers are heroes. So I'm really not throwing anybody under the bus. But this is an oversimplification that may happen in the gas phase, but in this class, we're interested in the world around us, which is not in a vacuum. It might be in a flask, it might be in water. What happens in water is that HCl transfers its proton to water to give you hydronium and Cl minus, okay? Now, the way that happens is actually a Homo-Lumo reaction. Lone pair electrons on the oxygen of water, the HOMO of water, attack the LUMO of HCl, which happens to be the hydrogen chloride sigma star, which looks something like this. And so as those lone pair electrons on oxygen dump themselves into the sigma star, we form a new oxygen hydrogen sigma bond, and we have to break the old hydrogen chloride sigma bond with the electrons ending up on chloride because chloride's more electronegative than hydrogen. So really, if you've thought about acids before, especially Bronsted-Lowry acids as being proton donors, what's really going on in aqueous solution is, yes, a proton is being donated to water to give you hydronium, but this is also an example of a Lewis base, Lewis acid reaction. And so for us, when we think about Bronsted acids and giving up protons, it's always going to be tied very closely to Lewis acid. A Bronsted acid is a Lewis acid where the LUMO happens to be a low-lying sigma star involving a hydrogen. All right, well, how can we tell which side of equilibrium wins? I suppose I might say that we could think about the reaction going this way, Cl minus coming and attacking a hydrogen oxygen sigma star in exactly the same fashion to go the other way. So which is more favorable? You can ask this question multiple ways. You can ask which acid is stronger by identifying both acids on either side of the equation. You've got HCl, which is our acid here. And then you have hydronium, which we'll call the conjugate acid of our base on this side, which is water. We'll call Cl minus the conjugate base. You ought to be really good given an acid drawing its conjugate base. You ought to be really good given a base drawing its conjugate acid. But asking where this equilibrium lies is the same as asking which acid is stronger, which is the same as asking which base is weaker, which is the same as asking which highest occupied molecular orbital is lower in energy, which HOMO of the conjugate base is lower in energy. We can tell this, I mean, intuitively, you probably already guessed, you know, HCl is a strong acid. So probably you're going to tell me that equilibrium is way over on the right-hand side, and you're right. How do we know that? Well, we look up what are called pKa values. We'll talk maybe next time about where the pKa value comes from. For now, it's enough to know that it represents how acidic a molecule is, how readily it will give up its proton. And it's a number on the logarithmic scale, and lower pKa numbers mean stronger acids. You may remember that from Gen Chem. The pKa of HCl is like -7, whereas the pKa of hydronium is -2. So that means that HCl is the stronger acid, and it's a stronger acid by a factor of like 100,000 times. So that tells you if HCl is the stronger acid and H2H3O plus is the weaker acid, what does that tell you about the reactivity of the conjugate bases? Which conjugate base is more reactive, water or Cl minus? You say water is more, oops, sorry, I'm on the wrong spot there. Water is more reactive, whereas Cl minus is less reactive. Okay, what's the reasoning there? Yeah, how do you, yeah, take us through the thought process.
Is a strong acid, so that means conjugate base has to be very stable. Otherwise it would dissociate completely.
Okay, good. So the reasoning is that a strong acid is strong because its conjugate base is very stable on its own. Look at what happens when a strong acid loses its proton. The electrons that were in that bond end up on the conjugate base. And so, how acidic something is related to how well that conjugate base can tolerate fully owning those electrons. Okay? Stronger acids have very stable conjugate bases. And so we will often rationalize the acidity of something by considering how stable its conjugate base is once the proton is gone. That's a really important point. So maybe I'll say it again. We're going to rationalize how acidic something is by considering how stable its conjugate base is once the proton has been removed. How well does that conjugate base tolerate fully owning those electrons that it used to be sharing? Okay? So maybe you can rationalize that here. The pKa data tell you that equilibrium favors the right-hand side and that HCl is the stronger acid. That Cl minus is a less reactive, weaker, more stable base. By the way, we're going to use those terms interchangeably. Less reactive, weaker base, more stable, lower energy, HOMO. All of that we're going to use interchangeably. So can you think of a reason why Cl minus might be more stable, less reactive, have a lower energy HOMO than does water? Go ahead. Octet rule? Okay, what are you thinking? Okay, so Cl minus does have a full shell. Let's think about water and see if there's a difference there. Maybe I'll draw out the whole Lewis structure of water. What do you think? I mean, I guess their oxygen does experience 8, though I guess your point is in Cl minus they're all on chloro instead of shared. Okay, what else? What other property do you think might help explain this? Yeah.
Does that have something to do with like polarity or like electronegativity?
Okay, does it have something to do with polarity or electronegativity? Let's actually think about that. What does electronegativity mean, by the way?
Just like it's pulling how much it wants electrons. Or wants electrons.
Okay, electronegativity means the likelihood or the ability of an atom to pull electrons toward itself. Okay. But atoms, but why would an atom pull electrons toward itself? Extra special social skills, charisma, go ahead. To become more stable. Okay, so electrons are more stable on more electronegative elements. Okay, I like that. But why? Why would they be more stable on more electronegative elements? I'm being the 2-year-old here, and I'm going to keep asking why until we get to because I said so, or perhaps some fundamental principle of the universe. So go ahead.
Well, we know like the noble gases are the most stable elements. They don't want to lose or take electrons, and so like all the most electronegative elements are like fluorine, chlorine.
Okay. So it has to do maybe with how close they are to obtaining the noble gas configuration. Yeah. Okay. Good. What else?
It also has something to do with like when you look at the molecular orbitals, like you're feeling like for some reason those coming together, it's going to lower the potential energy, or like feeling like when you look at those, sometimes two things coming together will lower potential energy or.
Okay. Right. I mean, that's why bonding actually happens, because you can take 2 atomic orbitals, mix them together, and get a lower energy molecular orbital. But even if we were just comparing just the atoms themselves, yeah, go ahead. Okay. So I'll repeat it for folks at home. What I heard, there is a difference in terms of how many protons are in the nucleus for more electronegative elements than less electronegative elements. Yeah, go ahead.
Has it to do with the effective nuclear force, like the ability for the protons to attract the valence electrons?
Okay, effective, very good, nuclear charge, I think is, or force, or whatever it's called. This is based on the idea that the valence electrons are not held as tightly as the core electrons. So, and the core electrons shield the valence electrons from the nucleus. So as you move across the periodic table from carbon to nitrogen to oxygen to fluorine, you go from 6 protons to 7 to 8 to 9. So valence electrons in fluorine experience a much more positively charged nucleus than they do in carbon. And that means that those valence electrons, by experiencing a larger charge, move closer to the nucleus and are therefore more stable. Okay? And actually atomic size within a row of the periodic table tracks with electronegativity. Fluorine is smaller, its electrons are held closer to the nucleus, and that's because of the greater charge of the fluorine nucleus than the carbon nucleus. So here's a useful way I've learned to think about electronegativity. because it's related to how close electrons around that atom are held to the nucleus, you can think of electronegativity as telling you something about the energy of lone pairs on that atom. For example, if we were to think about lone pairs on carbon versus nitrogen versus oxygen versus fluorine, and if this is energy, we would come to this kind of conclusion that electrons, lone pair electrons on fluorine are simply more stable there than they would be on carbon. All right? All right, how does that explain the trend we've looked at? Well, actually, before we go back to that example, let me illustrate how this can be useful in deciding how reactive something is. Let's have a molecule with a lone pair on carbon, a molecule that's negatively charged with a lone pair on nitrogen, a molecule that's negatively charged with a lone pair on oxygen, and then a negatively charged fluorine. Based on what we've talked about, which is the most reactive, least stable, highest energy lone pair? One on the carbon, right? And you know this because carbon's less electronegative. The most stable, least reactive, lowest energy electrons would be on the fluorine. And it turns out if you measure the acidity of the conjugate acids of each of these molecules, the trends track with what you would expect. HF is the most acidic. pKa is around 4, and that is because its conjugate base is the most stable, least reactive. Methane, CH4, is least acidic because its conjugate base is least stable, most reactive. It turns out the pKa for methane is like 50. Those are log units, so that's like 10 to the 46 times less acidic than HF is. And as you move across the row, the pKa values decrease. I think for ammonia, I got this wrong last time. It doesn't matter. You'll always have a pKa table to look stuff up on. For that NH bond, the pKa is about 38, so about 1 trillion times more acidic than methane. Water is 10 to the 22 times more acidic than NH3, and so on. So that follows our electronegativity trend. Let's go back up. Oh, before we go back up, any questions so far? So let's go back up to our example of HCl and we did a lot of examples. I'm getting confused. Let's look at our acid-base equilibrium between HCl and hydronium. Does electronegativity help us here? What do you know about oxygen's electronegativity versus chlorine? I think they're about the same. I mean, we could Google it. Hey Siri, what is the electronegativity of chlorine? Let's see if Siri can do this. Siri says the electronegativity of chlorine is 3 units of some kind. Okay, what is the electronegativity of oxygen? 3.4. Huh. Whoa, wait a minute. Oxygen's more electronegative than chlorine, so does that work here? Well, I guess you could argue, hold on there. This isn't fair because chlorine is negatively charged and water is not. Okay, fine. so let's do HCl plus OH minus versus water and Cl minus. Now we've got a great comparison. You know what happens there. pKa's would tell you that that's the case. Water is like 10 to the 23 times less acidic than HCl. But what the heck? The atom that holds the negative charge in the conjugate base is electronegativity of 3.4 here versus electronegativity of 3. So what? Why isn't electronegativity working here? Because our acid-base chemistry tells us that Cl minus is the more stable conjugate base. So why does electronegativity lead us astray here? Go ahead.
This is a guess, but is it because OH has like resonance? So no, I'm not sure.
No, so you're right that resonance can explain why, this is another reason why conjugate bases can be stable if they delocalize electron density via resonance. Though in hydroxide, there's really not any resonance structures to speak of. But we will see examples where resonance is the key. What else? Yeah.
A larger atomic radius for Cl.
Larger radius, larger size than Cl, smaller size. Okay, so what?
So they're naturally further distance, and there's also like more protons just in general.
Okay.
Yeah.
Right, so thinking about chlorine versus oxygen, the radius of chlorine is larger. And I guess there are multiple ways to think through this, but the most useful one to me is to go back and remember what atomic radius actually means. And that means sort of the average area within which most of the electrons are, right? So an atom with a larger atomic radius would have more diffuse or more spread out valence electrons. And we're going to see, pay attention to that spread out, we're going to see that electrons that are spread out have lower kinetic energy than those that are localized, and that can make them more stable. If you remember back to that awful bit at the first part of the semester where we were talking about wave functions and doing second derivatives and all of that business, the conclusion there was that the more spread out an electron was, the lower its kinetic energy. And so we would say that the electrons on chlorine have lower kinetic energy than they do on oxygen, and therefore they're more stable, despite the electronegativity difference. It turns out that when we see a size difference, a large size difference, we're going to ignore electronegativity. It's not going to work for us in terms of rationalizing acidity. The size issue and why that should be stabilizing can be difficult to think your way through. So if the whole second derivative thing isn't working for you, I'll try another terrible analogy. Imagine the difference between a small marble and a larger sponge. I wish I had a marble and a sponge. Maybe I can come up with those at some point, but I don't have them today. So a small marble, and maybe it can be one of those cool sort of ones with the swirlies and okay. Maybe it can, maybe it can actually be the evil eye of Sauron or something. I see you. I'm sorry. And then a larger sponge. And maybe this larger sponge has pants and he lives in a pineapple or something like that. All right, whatever. I don't remember other than he has kind of a large nose, and I don't remember if he had buck teeth or not, but we're going to pretend. All right, so we have a marble, the Eye of Sauron, and we have a sponge named Bob. And imagine taking a little dropper of water and putting a single drop of water on the marble, where it just sort of beads up and stares at you, versus putting the single drop of water on SpongeBob. Now, for this to work, we have to assume he's not actually still in the pineapple under the sea, but rather he's on the surface and he's been wrung out. Once you put the drop of water in the sponge, can you see it anymore? Where is it? It's sort of just spread out, right? And so the sponge feels less wet than the marble does. Where here being spread out is more, I don't know. I really tried, but hopefully you can see that that for atoms, being able to spread out their valence electrons over a larger area is a stabilizing thing. And so in terms of reactivity, Cl- is not as reactive as OH-, even though oxygen's more electronegative. When there are size differences, we'll focus on those instead of electronegativity. So that will explain why, as an example, if you compare HF versus HCl versus HBr versus HI down the periodic table, we are least acidic at the top and get progressively more acidic as we get to the bottom, and it has to do with the size of the conjugate base. So I- would be like Bob Sponge Esquire the Third, and F- would be the Sauron marble of doom. Anyway, so let's see if you've got this principle down. I'm going to write down in no particular order, what the heck? I think that's a real thing, but actually we'll put selenium there and sulfur there. Water, which we love. Hydrogen sulfide, which we do not, because it smells bad. And then hydrogen selenide, which I actually don't know what it smells like and haven't ever experienced. Can you tell me which is the stronger acid? Or, if you prefer to think in conjugate base, can you tell me which conjugate base is more stable? More stable conjugate base is the selenium one. Why? Size, it's just bigger, spreads out electron density, and therefore H2 selenium, hydrogen selenide would be more acidic. Okay, good. So that's a decent and useful principle that we'll call on again and again. There's some nuances here that we are ignoring. It turns out that how reactive these conjugate bases are sort of depends on the solvent you're in. So what I've told you is true. So what I've told you is true from a certain point of view, but it won't turn out to matter that much that I've oversimplified to you at this stage. So we'll pretend that the world is as simple as we've just laid it out. By the way, that whole certain point of view thing was really kind of a cop-out. Luke really let Obi-Wan off the hook for that. You know, he should have pushed a little bit harder. But I guess don't get me started on plot holes in the whole Star Wars franchise. But I guess it was always more about the spaceships and the lasers and the swords and the shooting and the explosions and the swashbuckling than it was ever about like compelling writing or dialogue. You will try. What? Sorry, go ahead. I might be on something. Yeah. Yes, my favorite line in the original trilogy is the line. Whatever. It's Friday. Is the line in Empire Strikes Back where they're fleeing Echo Base and Princess Leia explains that there will be 2 fighters assigned to each transport. 2 fighters against a Star Destroyer? Where did they get that guy? And looked like he was reading his lines from a big poster held just off screen. All right, sorry. And then there's Anakin. I don't like the sand. It gets everywhere. It's coarse.
Not like you.
Not like. Listen, if any of you choose a romantic partner that acts like that, please come talk to me before you make any life-altering decisions, okay? Somebody really should have pulled Padme to the side and said, all right. That was a diversion. I'm sorry about it. Bringing it back in, we've talked about the strength of conjugate bases in terms of their ability to tolerate extra electron density. We've developed 2 principles so far. Electronegativity is one way you can tolerate extra electron density because the electrons you have are lower in energy. And the second way is spreading out electron density through space, or delocalization. So there's a couple more demonstrations of this principle that we'll talk about. I want to do one, and maybe we don't need to spend a huge amount of time on it. It's another demonstration, really, of electronegativity. But I'm going to present some data for you. This is ethane. And we'll be talking about the acidity of one of ethane's protons versus ethylene, where we'll be talking about the acidity of maybe that proton, they're all identical anyway, versus acetylene, which is the alkyne. Those are actually non-standard names, ethylene and acetylene, but I don't care that much about nomenclature, so you don't need to necessarily know or memorize that. I suppose it's useful to know that this is an alkane, that this is an alkene, and this is an alkyne, but whatever. Let's now, and maybe I'll draw the bond so that we can be thinking about things. And I will give you some pKa information. For the alkane, as we've said, it's 50. For the alkene, that proton has a pKa of about, I don't actually know, is it 45 or is it 40? I'm going to make something up. It's 40. You can look it up in the pKa table. I don't have you memorize pKas. I think there are a couple you should know. But in any case, you're going to have access to the text during your exam, and at least until our robot overlords deny us access to the World Wide Web, memorizing numbers will not be that useful. So we won't worry about that as a skill. The pKa for the alkyne is around 25. So there's a huge difference as we go from alkane to alkene, and another huger difference as we go from alkene to alkyne. Let's talk about why, and perhaps in so doing, let's just draw the atom that holds the negative charge in the conjugate base. Yikes. Versus this one. All right, so we've drawn each of the conjugate bases. There's no real size difference. Carbon is sort of the same size in all of those structures, maybe small differences, but not huge. So what do you think's going on here? Go ahead.
Is it the same thing that has to do with electron density as we're producing more and more pi bonds or adding more and more electrons into a smaller space?
Okay, does it have to do with delocalization? If we have more pi bonds, is the molecule smaller and therefore we're cramming molecules into a smaller space? That sounds reasonable, though I suppose it would lead us to the opposite conclusion, because localizing electrons increases their kinetic energy. So I think that would lead us in maybe the opposite direction. What differences do you, I mean, all those atoms that hold the negative charge in the conjugate base are carbon. What differences do you notice about those carbons? I mean, the double bonds, obviously. What else? Go ahead.
Does it have to do with hybridization?
Hybridization. Okay, so what differences in hybridization do you see?
So the first molecule would be sp3 hybridized, the second one would be sp2, and the third one would be sp.
Okay, so how did you know that, for example, that carbon would be sp3 hybridized?
Because the original one had 4 distinct bonds.
Okay, so the original molecule had 4 groups around that carbon. We removed the proton and there's still a lone pair left behind, so there's still 4 things around that carbon. So you're right, that carbon would need to be sp3 hybridized, and for similar reasons, the carbon that holds the negative charge here in this conjugate base would be sp2, and the carbon that holds the negative charge in the conjugate base over here would be sp hybridized. All right, so that's a difference. So what? What difference should that make? Go ahead.
Because the SP has more S character, it's 50%, it'll be more stable because they're all concentrated around the S orbital rather than the P, which is higher energy.
Okay, so a lot of good stuff there. 50% S for the SP, whereas SP2 would be like what, 30-ish, 33. Just as a math question, it's not hard, Joshua. If there are any Joshuas here, I wasn't talking to you, I was talking to myself. I don't think that makes it better, actually, but there you go. All right, but why should S character matter? You said something about more stable. What do you know about S orbitals versus P orbitals? Go ahead.
S orbitals are spherical, so the electrons are better localized around the nucleus, whereas P orbitals are fast on the side.
Okay, yeah, so I'll repeat for those of you playing along at home. The S orbital is spherical and holds electrons closer to the nucleus, whereas the P orbital has a node at the nucleus and therefore has to hold the electrons further away by definition. And you're used to thinking about this from Gen Chem because we start to fill S orbitals before P. If you want to think back to our original discussion of what the S wave function looks like, if this is wave function and this is distance from the nucleus, the S orbital, this is the 1s orbital, has maximum electron density at the nucleus, which is crazy. It doesn't spiral in and explode, but it can be there. Of course, a 2s orbital looks a little bit different. It has a node at a certain radius after the nucleus and then picks up again and tails off, but it still has a large finite electron density at the nucleus. In contrast, if we're to look at a p orbital, and in this case, let's be looking at the p orbital along its longest axis. It's negative on one side and positive on the other, but at the nucleus, electron density and wave function both equal 0. So by definition, electrons that are held in p orbitals have to be higher in energy than those that are in s orbitals because they're held further away from the nucleus. And this is true even for the hybrid orbitals. So if we start to mix S and P together, it's just sort of an averaging thing, right? sp hybridization comes by mixing an s orbital with a p orbital. So it's going to be 50% s and therefore lower in energy than the sp2, which has 2 parts p and 1 part s, 33% s, versus 25% s, which would be highest in energy. So because an sp orbital is lower in energy than an sp3 orbital, conjugate base in which the negative charge is held in an sp orbital should be more stable than one that is held in an sp3 orbital. It's all about orbital energy levels. And remember that actually electronegativity was about that too. At the very beginning of class, we talked about how electrons on more electronegative fluorine actually are lower in energy than they would be on a less electronegative element. So if you want to, you can think of sp3 carbons as being way less electronegative than sp carbons. That for the reasons that we've described, but if you need a tool to remember this kind of trend, it can be, oh, well, orbitals with more s character are more electronegative and are therefore lower in energy. It's sort of hard for me to think of how I might write a more complicated question about this type of trend than what I've told you. Explain why the alkane is so much less acidic than the alkyne, and you could probably do it without a lot of trouble. All right, I haven't paused yet for questions from our friends at home. Anything TAs in the chat that I need to address?
They're answering the questions in the chat.
More some Star Wars analysis, but I don't know if anybody else agrees.
Okay, so there's been a request for more Star Wars analysis. Good. Well, I'm happy to oblige, but actually, maybe what I will do instead is, I actually do have a Darth Vader costume. There was a time, back in 2019, I think, when we were still able to travel, I was going to Wisconsin to a seminar, well, actually a birthday party for my PhD advisor, and his favorite thing he wanted to do at his birthday party was to have a science seminar, which was actually fun. It was a group reunion. But in any case, I got bumped off a flight, got a $800 Amazon gift card as a gift, and so I went and bought this Darth Vader costume off Amazon. And it's awesome, though perhaps not as awesome as you would expect for the money that was paid for it. In any case, Dr. Michaelis and I are both sort of Star Wars geeks, me more so than him. He kind of likes to play along. And so for Halloween last year and the years before, we've put on a little bit of a show involving my Darth Vader costume and my lightsaber that glows and makes sounds that I keep up in my office. Maybe I'll bring it next time. But if you want to see this year's production on Halloween, just go to my YouTube channel where all the lectures are posted and scroll down a little bit, and there'll be something about Kylo Ren and Darth Vader. The production value this year was way higher than it's been in years before. There was music, there was dialogue, there were explosions. I almost caught on fire, and our fake lightsabers looked really awesome through the Zoom camera. So you can go watch that, and then maybe we can talk more about Anakin. And we can talk whether it was a good idea or a bad idea to bring back Emperor Palpatine and all of that stuff. Yeah. Okay, well, So we've talked about electronegativity as being where electrons can be low in energy. So let's go all the way back to the example we started with at the beginning, our friendly neighborhood molecule with both an alcohol group and an amino group. With what you know now, tell me which are the highest energy lone pair electrons in that molecule. While you're thinking, I will just recaffeinate. Okay, what do you got? Go ahead.
The ones on nitrogen.
The ones on nitrogen. That is correct. Ding, 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 ding. So, why?
Because oxygen is more electronegative. So the ones on nitrogen are less stable and more reactive.
Okay, good. So I'll repeat that for our friends at home. The ones on nitrogen, because nitrogen's less electronegative than oxygen, that means the electrons on oxygen are held lower in energy, more stable, less reactive. Okay, so now it's actually no longer a problem to look at that molecule and say, okay, which is the highest, which is the HOMO. If you had to pick, you'd say non-bonding lone pairs on nitrogen. But I'm not going to ask the question that way. I might ask which is the most basic lone pair, or which is the most reactive lone pair in this molecule. All right? So maybe I will give you an example to think about. And so actually, I want to talk about another way that conjugate bases can be more stable. And we're going to do this by contrasting the molecule ethanol versus the molecule acetic acid. Ethanol, of course, is drinkable, but not here. You can get it from fermenting grapes, and if you let them ferment too long, you can actually make vinegar or acetic acid. Ethanol apparently has various depressive effects on the central nervous system, whereas acetic acid is just sour. And maybe good in some dressings called vinaigrettes. In any case, there's a difference between the two, right? Let's look at their conjugate bases. And I want you to think about the differences. I guess we don't have time to talk about them now. But I want you to think about the differences between the two. Can't be atomic size, because the atom has the same size that holds the negative charge. Can't be electronegativity. They're both on oxygen. What else is it? Go ahead.
There's another lone pair.
Oh, sure. There's actually lone pairs here, too.
Oh, but also just saying the difference with taking off the hydrogens, that the hydrogen is another lone pair, so that affects the energy.
Oh, so the question is, I'm not sure I understand the question. Are you asking if I remove this hydrogen, do I have more lone pairs over here than I have here?
Comparing the two?
Oh, just comparing the two. In terms of the actual oxygens, no, they have the same number of electrons. I suppose you could argue, though, that there's a nearby oxygen here that isn't present here, right? That might have an effect. But yeah, there's something going on. Go ahead.
The one on the right has resonance structures that can stabilize.
You've got the opportunity for a resonance structure over here on the right, which tells you, sort of like our allyl anion system, that negative charge can be delocalized on both of the oxygens. Spreading out is more stabilizing. So we'll talk more about that next time. That's just a preview. Sorry to go over just a little bit. My apologies. I hope you have a great, fascinating weekend. Fascinating, no, may it just be great and uneventful. Fascinating maybe sounds dangerous. So anyway, talk to you next time.